The next thing we're going to look at here this morning is going to be a compressor. And the compressor is almost the opposite of a turbine in many ways. A compressor requires power to run, and it will, instead of there's going to be expansion inside of it, there's going to be compression. You're going to compress the fluid going on to it. So here a compressor, there's work being done on a flowing gas to change its state. Okay. Now the key word here is gas. Okay. A compressor is going to work on a flowing gas. We've often talked about a pump. A pump is the same thing. It's going to be work being done on a flowing, it's going to say liquid to change its state. That's the only difference between a compressor and a pump. They're very similar in how we're going to draw them. And so if we look at what we're going to have, oh, there's me double, there we go. Here's a bunch of compressors. You're used to maybe seeing an air compressor where the compressor unit, you're going to have this compressor that's going to be coming up here. It's going to be belt driven or some sort of way that we can run the compressor. We're going to be concentrating on the air coming in and coming out and getting stored in this tank. We're only looking at this top portion of this. Top portion is what we're going to be working on. And there are so many types of compressors. I mean, you can look up here. Here's your refrigerator compressor. Looks differently as it's compressing a refrigerant. This looks like a big black module in the back of a compressor, the back of your refrigerator. You will see. Let me see if I can find there's all sorts of different compressors here. The one compressor that you might see a little bit, a compressor on a jet engine. Let's say on a jet engine. These compressors look very similar to what turbines do. They look very similar to there. You're going to have vanes and a stator and a rotor as the air comes in. So many different types of compressors, again, just like there's different kinds of turbines that you'll be dealing with. Okay, so now let's go back to the lecture video and let's see if we can't analyze this a little bit. So a compressor, when I draw a compressor here, I'm going to draw it opposite of what I did with a turbine, because I'm compressing it so that trapezoid is going to go down. I put a big C here, and then I'm going to have my shaft coming out of here, and here's going to be my power coming in, and this is going to be state 1 coming in and state 2 going out. Okay, that's going to be my compressor. If I want to draw a pump is probably going to be, I'll draw a circle here with an outlet and an inlet. I'll put a big P on it, and here is going to be state 1 coming in and state 2 going out. So this is going to be just how the difference in drawing these two schematically. Now I want to draw a TV diagram for both of these as well. So here would be my TV diagram for my compressor. I'm going to have two pressures, pressure 1, or let me just do it this way. It should be this way. It should be pressure 1 and pressure 2 because I'm going to be increasing my pressure. And so I'm going to go from state 1 to state 2. Okay. And we can see as we pressurize something, the temperature is going to rise, and we are going to decrease the specific volume as we compress it. Again, we don't exactly know the path. When we deal with a pump, in our TV diagram, we're going to have our vapor dome, and we're going to have our lines of two pressures, so pressure 1 and pressure 2. And we are going to be over here in the liquid portion of things, so we're going to be dealing with state 1 and state 2. You know, we're going to be going, it's almost going to look straight, going like we're going straight up there, because the specific volume probably won't change a little bit, but it might modify. You might compress it just a little bit, but usually we're changing, the pump is not changing the specific volume as much as it's changing the Z height, how high we're moving. We're not usually changing the temperature a lot, so this is an exaggerated diagram. Usually those lines I probably should draw my lines a little bit better. If I were to draw this accurately, it would come down. This would come down just pretty much parallel. Sorry, pretty much perpendicular to that saturated liquid line. So you're not seeing a lot of change in temperature, but you are going to see a change in that energy that you're putting into it, which will allow the potential energy change to happen there. Okay. Now let's look at what we're going to look at for our pump or our compressor. We're going to start with our energy equation. dEcV dt is equal to Q dot minus W dot plus the summation of my mass flow rates N times my enthalpy N, my kinetic energy N, and my potential energy N, minus the summation of my mass flow rate exiting times my enthalpy exiting, kinetic energy exiting, plus my potential energy exiting. Okay, I'm going to look here, and I'm going to say first I'm going to look at a compressor. Okay, our common assumptions that we're going to make. So our common assumptions. We're still going to say number one, that's going to be steady state. See, that's going to make the change in energy of our control volume go to 0, so that's going to go away. Common assumption 2, we're going to say that our potential energy is approximately equal to 0. We're not going to be working about potential energy changes. There's just not a significant amount of potential energy change. And again, we're going to have 3, that our kinetic energy is approximately equal to 0. This is unless a velocity is given. Just like before, just like a compressor. It's a lot of similar things that we go there. And again, I encourage you to put a velocity change into your kinetic energy equation and see how much change a kinetic energy will give. When is kinetic energy not negligible? In fact, I think I'm going to make that an alternative homework assignment. I'm going to ask you to work on this and figure out how much change in velocity before the kinetic energy even provides any change to our answers. Okay, so I'll get rid of that, and then of course here's I'll say often we'll have that Q dot is equal to 0 if we have an insulated situation. So this will go away as well. But again, I want you to work through it each time. Now what that gives to us is we're going to get that W dot of a compressor is equal to M dot times H1 minus H2. It's the same equation that we have for a turbine. What the difference is in this equation is that your enthalpy at state 1, so here enthalpy at state 1 is going to be less than the enthalpy at state 2. And so you will have that a power is going to be required, or a negative power. Q dot or M dot W dot is going to be negative. So often what we do in these problems is we'll say that W dot of the compressor is equal to M dot times H2 minus H1. You will often see this where they will say compressor, and you will know that a compressor requires power. And to do that, what they'll do is they'll flip the order of H2 and H1 and give you the magnitude of the power needed for the compressor. Okay, so understand that if you see this, if you see a compressor and you see that the enthalpies are switched, H2 before H1, they're doing that just to give you the magnitude. Okay, they're given to you just to choose the magnitude. Okay, now that's what we're going to deal with the compressor. Now with the pump is going to be different. The pump is different in that it's going to be the same as a compressor, but now potential energy is not negligible in most situations. Okay, that's where it differs from that compressor. And so what you're going to have here is you're going to have 0 is equal to W dot or minus W dot of the pump plus M dot times H1 minus H2. I'll put square brackets here. Plus G Z1 minus Z2. You will always have that potential energy change. And so you need to make sure that when you're dealing with a problem with a pump that you know what your datum is, what you're considering state 1 and where you're going to be state 2. So sometimes they'll give you the height they want to pump the liquid to. You have to know that delta Z, what that is. Is that Z1 minus Z2, or is that Z2 minus Z1? How do you put that into this equation? That sign is going to be very important. So please pay attention to that. And of course, pay attention to your units as you do the conversion when you're dealing with the pump. Okay, so pumps and compressors. Those are going to be the second type of control volume that we will talk to you about today.